I got my PhD at a school down the road, as you know, that you might know about. Madhu also used to work there. He was my PhD supervisor. And I remember one time a very illustrious professor called Ron Raz, who's very famous in computer science, came to give a talk. He lived in Israel at the time, but he came to Cambridge to give a lecture to us. And after the talk was over, Madhu took, Ron Raz and me and other people to the Cambridge Brewing Company, as he would always do, since that's his favorite place. And Ron Raz did not know who I was. I was just like a lowly student at the time, but he's a very nice guy and polite guy. And so to make conversation, he asked me what I worked on in my research. And I said, Boolean functions. And he laughed uproariously because he was like, everything is a Boolean function in computer science. Like, every topic is a Boolean function. And I guess you covered exactly this fact in like lecture 3 or something. Like everything that you might ever want to compute on or care about under the sun can be encoded by like a Boolean string, and everything that you want to actually compute can be encoded upon by a Boolean function. But it is true that as I sort of said, I am interested in the Boolean functions and still am, but in particular, I'm interested in using this particular tool for studying Boolean functions, which is Fourier analysis of Boolean functions. So that's what I'm going to tell you a little bit about in this talk or lecture. Okay, so right, Boolean functions, or I think you were calling them like finite functions in your class, but I call them Boolean functions. So a Boolean function is a function f that maps n-bit strings into, let's just do 1-bit outputs. You can think about functions with multi-bit outputs, but let's just focus for this this lecture on 1-bit outputs. And the most simple way to encode a Boolean function itself is by its truth table. So you can encode it by a truth table. Okay, and so what does a truth table for an example Boolean function look like? Well, let's do an example where n equals 2. There's 2 input bits. So truth table has, all the possible inputs x, which are all the 2-bit strings, and the resulting 1-bit output f. And the strings are these ones. I'm going to write them in a funny order in this talk, but it doesn't matter what order you write them in. And here are the outputs. Okay, so finite functions, if I'm checking the chat now, finite functions if the domain is finite. Okay, yeah, in this talk, all the domains will always be finite. Great. So this function f has a name. Please type it to me in the chat, and then we'll know that we're on the same page. This function has a well-known name. So that's one example we can consider with 2-bit functions. The AND function, yeah, I didn't do the NAND function. I know you all are like super obsessed with the NAND function in this course, but I just stuck with AND for simplicity. That's AND. Sometimes I might write a little subscript to denote that it's on the AND function 2 bits, because you can do the AND function on lots of different numbers of bits. Let's do another example where n is 3. This is maybe my favorite example, or one of my favorite examples, if anybody can be said to have a favorite Boolean function. So n equals 3, so I will like explicitly write it all out, all of the great rows of this truth table. Okay, let me write the answers in red. Okay, so take a look at that truth table, and you can also tell me what it's, well, a name for it, or what function is being computed here. What's f's name? Oh, majority. You guys are very quick on the ball. Oh, this is amazing. I got like 4 people answering me right on the spot. Yes, that's right. I wrote it in like I wrote these strings on the left in like a slightly non-standard order because it makes it easy to write the answers on the right. Yeah, this is the majority function on 3 bits. It's just 1 or 0, depending on whether, excuse me, the majority output is, majority input bit is 0 or 1. Oh, I'm going to solve the problem set problems. That's great. Yeah, I have no like vested interest in this class. I'm happy for everybody to learn. Just start typing your problem set problems into the chat, and I'll try to solve them on the side as we go. I don't care. Great. So one thing I'm going to do in this lecture that's going to annoy you a little bit, but we got to do it, is, yeah, sorry, this is majority. Majority on 3 bits. Because you could also take majority on 3, any odd number of bits. I'm going to make the output be described by not plus or 1, but I'm going to make it 0 and 1, but I'm going to make it described by -1 and +1. It's quite common in like machine learning, where like you think of like the input string is representing some object, but then each object is either positive or negative. Okay, so I'm just going to call the output bits plus or minus 1. And actually, it'll help distinguish between input bits and output bits. So let me erase everything here. And like this is going to be minus 1, minus 1, minus 1, minus 1, plus 1, plus 1, plus 1, plus 1. Okay, and I guess I should erase these ones here as well. Minus 1, minus 1, minus 1, plus 1. Okay, so I guess in the rest of this lecture, that's how we're going to be describing Boolean functions. Great. So also, please tell me in the chat, if you would be so kind, I know you all know this, but just so we're on the same page, how many rows a truth table will have if it's a function of n bits. So f, function on n bits, which I guess now we're going to write like this. It's going to map strings of zeros and ones into minus 1 and plus 1, has a truth table with, now I'll look up at the chat, 2 to the n entries. Thank you very much. Yes, that's right. 2 to the n numbers. It's a very large number of numbers, but it's okay when n is 2 or 3. Okay. And now I'll tell you about the subject of this lecture, which is, as I mentioned, Fourier analysis of, let me write it in a lurid green color, Fourier analysis for Boolean functions. The basic story of Fourier analysis of Boolean functions is that there's a different way to encode a Boolean function like f by a list or table of 2 to the n numbers. Excuse me. So yeah, for every Boolean function like this, every finite function like this, you can just write down its truth table. But what I'm telling you is you can also write down a different list of 2 to the n numbers that somehow also represents the function. And thinking about these two different representations turns out to be very fruitful. So let me just start by just telling you, without explaining, what is the different list of 2 to the n numbers. In these two cases, we saw the AND function on 2 bits and the majority function on 3 bits. So I'll write it over here. And when you have the different list of 2 to the n numbers, you call, instead of calling the table by f, you call it by f with this, it's called a hat for some reason, even though it's just like a, I don't know, a carrot or something. F hat is sort of the name of the list of the alternate list of 2 to the n numbers. And it looks like this, 0, 0, 1, 0, 0, 1, 1, 1. And here are the numbers in this particular case. Negative a half, negative 0.5, negative 0.5, negative 0.5, and positive 0.5. Okay, so this is for the AND function. This is the alternate list of 2 to the n numbers, or 4 numbers for this function. Okay, and I'll also do it for the majority of 3 function. So actually, since f's name here is majority of 3, I can write majority of 3 with a giant hat on it. And let's do it. I'm going to write it all out. I'm going to get good at this. 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1. Okay, so here are the 8 numbers that are the alternate representation for this majority of 3 function. So it's a 0, 0.5, half, 0.5 again, 0.5 again, 0, 0, 0, and negative 0.5. Okay, so those are the numbers for the majority function. In general, as I said, for every Boolean function, we'll have like a different way of encoding it using these like green numbers rather than these red numbers. These green numbers will, you can see they're not necessarily integers. They're not zeros and ones. They're in general fractions. They'll always be between -1 and +1. Okay, so I'm not going to ask any questions, which one normally does periodically in a talk, because obviously you have questions. So I'll address your questions. First question you obviously have is what? And then the second question you would probably have is how? And then the third question you'd probably have is why? So I will try to answer these questions. What's going on? And what is this list of numbers? And then how do you get this list of numbers? And then why would you want to get this list of numbers? Excuse me. I have a cold. Okay, let us start with what. But seriously, if you do have questions, feel free, as I said, to type them into the chat. So this is, as I said, these green numbers, or these alternate list of numbers, are somehow a Fourier transform for a Boolean function. And I expect or wager that you've heard about Fourier transforms or Fourier series at least at some point in your life. I don't know, like in some popular physics thing or some actual physics thing or some engineering class or some math class. You probably heard about Fourier series. And if you haven't, it's fine. But if you have, I'm just going to try to make an analogy which will explain why what we're going to talk about here is like Fourier transform or Fourier series, but for Boolean functions. So it's a very computer science-y version of Fourier series. So I don't know anything about like physics, by the way, but so I'm just going to repeat some physics things that I was told by YouTube videos. Let's say that you go to a piano and like you mash, your fingers on the keys and you make like a chord, or you somehow like in life generate some beautiful sound. Then what is sound? I'm told that it's like somehow just like different air pressures, like pulsating in time, and like your ear transforms these pulsating, different air pressures to sound or music in your brain. So somehow like, okay, let me make a plot here. When you smash those notes on the piano, you have like you have a plot for how it changes like the air pressure near the soundboard. And so like maybe it looks like this. I'm just drawing like some bogus example here, but I don't know. Okay, so you'll get some, like if you just play a chord or something, you'll get this like repeating air pressure pattern. So I mean, I guess it can be positive or negative, like the air has more or less pressure as time goes on. Okay, and like that somehow like represents sound. But there's this thing called, for example, Fourier series in math, which says that like if you have any function like this red function of like, this is a plot of like air pressure over time, you can kind of like decompose it into a combination of like sine waves or like sines and cos waves or something. Okay, so again, you don't have to exactly understand what I'm saying because I don't exactly understand what I'm saying. I know when we get to the computer science version exactly what I'm saying, but any pattern of a function like this can be decomposed in these things that are like pure frequencies or like sine waves. So this is like sine wave is like a pure tone. Like if this is repeating at like 440 times per second, it's like a pure tone. It's like what you get if you just like press one key on a synthesizer. Like that's the purest tone. It's like this sine wave. Okay, but like the actual sound you get is not like just a pure tone. It's like a combination of pure tones. And they have different, I guess, frequencies they're called. They all look like sine waves or cos waves. So maybe it's like this. And then maybe like this. And actually, you don't have to just add them up. So you can add them up with different like weights or like intensities. So these are like, I don't know, like 3 purest tones that you might get if you hit the key on the synth. And like, you can like add them up with different weights. So like maybe you take this one with intensity 0.6, and then you add it. And maybe this one you take with intensity like minus 0.3, and you add it. You take this one with intensity like 1.2, you add it, and like it equals this original pattern. Okay, it's probably like a crazy shape like this actually is not just the combination of 3 simple pure sine waves, but let's just stop the example there. Okay, and so these yellow things are like the volumes or the intensities of these different like pure tones that like make up this glorious sound, and it's like just a fact of math that every function, every pattern of like air pressure over time can be decomposed into some of these like very special patterns, these very special orange, simple functions. They're like sine waves. And this topic Fourier analysis for Boolean functions is going to be like a very similar thing. We're going to take like any old Boolean function that you might be interested in computing, and we're going to represent it as like a combination of like different intensities or strengths of some other very simple Boolean functions that'll kind of be like analogs of these sines and coses. Any questions right now? I'm going to try to draw another picture to explain what I mean. So in the Boolean world, the world of Boolean functions, okay, they're not so easy to plot a Boolean function, but well, if it's only a 2-bit Boolean function, we can kind of like make some sort of funny plot. So here is, I would say 0, 0. These are the 2-bit possible inputs, 1, 0, 0, 1, and 1, 1. Don't need that. And let's take the AND function. So it's like the AND2 function. This is +1. Remember, our outputs are now are plus or minus 1. Kind of looks like this. I mean, it's funny to draw it with like a histogram. It's like, so there's only 4 possibilities like this, but you know, this is like a plot of the AND function. Yeah, as Madhu says, the red plot is like the red truth table. This is actually like a giant truth table. Like if you like, of some kind of truth table, if you like cut up time into really, oops, I should use black. If you cut up time into like really discrete increments, then like each time has like a height. And you could list those heights as numbers. They'd be a bunch of positive and negative numbers. So it looks like more complicated in some ways than like, I don't know, a truth table, because, well, the heights are not just plus or minus 1. You know, you can have any height. And there's like all sorts of, I don't know, maybe you have like zillions of different time intervals. But yeah, that's the analogy. So for Boolean functions, I mean, you could draw some sort of like weird plot of like the truth table as I've done here. You know, I don't know, wrote all the strings out on the horizontal axis, and I wrote the function value as like a little histogram bar, and all the heights are plus or minus. And right, so the sort of fundamental aspect of Fourier analysis for Boolean functions is that every Boolean function like this can also be decomposed into like a bunch of combinations of these like special simple functions or analogs of sine waves. And these sine waves get replaced by XOR functions. I believe you studied XOR functions today, and maybe you studied them like in an earlier class under the name odd functions or even functions. I'm not even going to get into the exact definition because it's like not super important. But let me just draw like a real quick picture. So this AND function on the left is going to be like the combination of like 4 simple functions. Again, the same plot, 0, 0, 1, 0, 0, 1, 1, 1. This first simple function is like a real simple function. It's +1 everywhere. That's 1, that's -1. And the next one, okay. I mean, every function on 2 bits is a pretty simple function. So it's kind of funny to say that these functions are just stressed that these are like the simple fundamental functions, but they are. So the second one looks like this. And the third one looks like this. Okay, and the fourth one looks like this. And this one down here is sort of like the XOR function on 2 bits. It's +1, -1. Remember, this is 0, 0, 1, 0. Or maybe it's the negation of the XOR function. It's not very important. But you see, you know, you get one value, in this case +1, when the XOR of the 2 bits is 0. That's the 0, 0 case and the 1, 1 case. And you get the other value, -1, when the XOR of the 2 bits is 1. Okay. So actually, again, this is not going to be super important, but I call this function XOR subscript 1, 2, because the function is you XOR the first bit and the second bit. And this function I call like XOR sub 2, because you just XOR the first bit with itself, by itself. And this one I call XOR sub 1, because you just XOR the first bit with itself. And this one's kind of like XOR sub empty set, because you don't XOR any bits together to get the result. It's just always +1. So, I mean, don't squint too hard at this. It's not going to be super important. But now I have to tell you the coefficients. So you add up this one with coefficient negative 0.5, and this one times negative 0.5, and this one times negative 0.5, and this one times positive 0.5. Okay, and you add these all up. And well, as I'm blabbering on, you can like take my word for it, if I didn't screw it up, that if you sort of multiply this first plot by negative 0.5, and the second one by negative 0.5, and the third one by negative 0.5, and the fourth one by positive 0.5, you get the histogram on the left. And this is in general what's going on with this Fourier analysis of Boolean functions. You're taking any Boolean function and taking this special set of basic functions, which are these like XORs of subsets of the bits. And you're trying to express the function, the red function that you care about, as some kind of combination of these basic XOR functions with like different intensities or different weights. And this list of like intensities or weights, which can be positive or negative, are exactly these like green numbers in the list. Okay, so if you remember up here, I told you this list was negative a half, negative a half, negative a half, positive a half. And it's a similar thing with this majority function. You know, there are like 8 special XOR functions, and if you combine them with these different intensities, you get the majority function. So I don't actually want to get like into the brutal details of like checking all that, but and defining like the XOR functions and everything, but I kind of hope the idea is clear, but this would be a good time for a clarifying question. Okay, so one person asked, can you explain the graphs for XOR1 and XOR2? I thought if you XOR the same element twice, you would always get false. That's true. Yeah, I was wondering if I could get through this without giving the definition. Maybe it was bold of me to think that I could do that. I'll give the definition. I think well, yeah, let's try to give the definition real quick. So if you have a function, you can have the function like, okay, let's say you have 3-bit functions, like majority of 3. Then you're actually going to have like 8 special orange functions, which I call the XOR functions.
Ryan,
and like one of them. Sorry,
Ryan,
go ahead. Yeah,
do you want to just use XOR as sum or 2, and that'll...
Sure, yeah, I'm never sure like how to describe XOR. XOR is like adding up numbers and then taking them mod 2, or it's like just checking whether the number of ones is even or odd. But the point is that you have you don't just like XOR together all the bits or take the sum mod 2 of all the bits necessarily. So one of the special functions will be, for example, what I call XOR subscript, this bits 1 and 3. And this is the function that like takes in 3 bits, like A, B, C, and because of 1 and 3 here, it just XORs together bit number 1 and bit number 3. Like it adds them up, or adds them up mod 2, or checks if there's like an even number of ones within this set A and C. Or if you're talking about like 5-bit functions, like one of these XOR functions might be like 1, 2, 4, 5. That takes as input like 5 bits, A, B, C, D, E, and you look at bit positions 1, 2, 4, and 5, 1, 2, 4, and 5, and you do like the XOR of these bits. So like you add up A plus B plus D plus E mod 2. Or equivalently, you just check if they're like an even or an odd number of ones among A, B, D, and E. So yeah, so if you have like, if you're talking about 5-bit functions, then for every different subset of the positions 1 through 5, S, you can define what I call an XOR function on S, which I write like XOR sub S, where the function like looks at all the bits in the positions defined by S and XORs them together. But if you didn't quite follow that, like don't worry too much. I mean, it's like, let me just assure you that, if you have, if you're talking about like, let's say 3-bit functions, and you want to do Fourier analysis for 3-bit functions, like the majority function, there's like 8 special functions, these 8 different orange XOR functions. And Fourier analysis is all about trying to express the function that you care about, this red truth table, as like combinations of the special XOR functions with different weights or intensities. But since we're not going to like really dive into like the details, it's not super important. It's like if I were trying to hide the definition of sine and cos from you, which is sort of what I'm trying to do. It's not that complicated, but I somehow felt I could save time by not getting into it. So actually, I mean, for most of what I'm going to talk about in the remainder of this lecture, in some sense, all you really need to know is for every Boolean function represented by like a truth table, like these red numbers, there's some equivalent way to represent it by 2 to the n numbers, these green numbers. And these green numbers are called the Fourier coefficients. And they measure like the sort of the strength or intensity of these different XOR functions within your function f. So let me move on to the question of how do you get these numbers, or how can you compute them? Well, I'm not going to exactly tell you because, as I said, I kind of was slightly sketchy about what even these XOR functions are. But I'm just going to tell you some facts about the situation. So again, let's say you have some function that you care about, like the majority function on 3 bits. Which has a truth table that looks like this. And I told you that like now we can call them, we can call them the Fourier coefficients, which is this other list of green numbers. I just told you these values: 0, 0.5, 0.5, 0.5, 0, 0, 0, minus 0.5. So how do you get them? Where do they come from? How can you go back? Well, I'll just tell you, if you have the whole truth table in front of you, like you have this whole list of red entries in front of you, it's actually very easy to get the green numbers. Given the whole truth table, there's like a very simple algorithm. It's fast, it's efficient. You can even like do like a really, really simple like recursive algorithm to find the green numbers. It's very easy to get the green Fourier coefficients. Now again, we haven't addressed why you would care to get these numbers exactly, but I'll claim that it's important and we'll come back to it later. But this sort of relies a little bit on this word given. So I mean, remember, this truth table is 2 to the n different numbers. And so is this set of Fourier coefficients. It's 2 to the n different numbers. So if, n is like 10, so 2 to the n is 1,000, I guess 1,024, it's very fine to like just, list off the 1,000 truth table entries. And then you can do a simple algorithm that lists off the 1,000 Fourier coefficients and you're done. That's fine. But I mean, one theme of presumably the course that you're taking right now is we have to care about like the complexity of things when the input size gets very large. And this is fine for, if n is like 10, but usually you're computing on, I don't know, inputs of size 1,000 or 1,000,000. So I mean, it's certainly impossible to like think of things this way. Let's say to do this, if, I don't know, n is bigger than or equal to 100. Because you don't even have like enough space in the universe to write down 2 to the power of 100 numbers. 2 to the 100 numbers is super huge. So you cannot just write down these Fourier coefficients. And you also can't write down the truth table of a Boolean function if it's on like 100 bits or something. But that's okay, because actually really in life, when you have a function that you care about, you don't really normally just write down its truth table. Of course, because this truth table is enormous. usually you have like a program or a circuit that computes the function. So that's usually the sense in which you like are given a function, that you have a function you care about. You're like given like a Python program that computes it, or I don't know, one of your NAND gates circuits that computes it, but you have some kind of program or circuit for a Boolean function. And that's how we normally kind of think about having a function that we care about. You know, there's some kind of box, maybe it's a circuit, or maybe it's some code, who can say. But the point is, it takes in like a bunch of input bits, you know, n zeros and ones. That's the input. In my little example, it just outputs one output bit, which is either, well, you can call it 0 or 1, or we've been calling it +1 or -1. That's the normal sense in which you kind of like have a function that you care about. And you might ask, like, okay, if this is how you have your function, can you get the Fourier coefficients? Again, please take my word for it that this is something that you're going to care about. I'll explain why shortly. And well, again, obviously the answer is no, because you can't just list them out. There's, you know, if the n is 100, there's 2 to the 100 of them. You could never write down 2 to the 100 numbers. But there is something you can do. So I'm just going to like tell you a fact now. There's a clever algorithm and fast algorithm due to two famous computer scientists called Goldreich and Levin from 1989, before you were all born, but not that long ago, to get all the large Fourier coefficients. And I'll explain what I mean by this in a moment. And in some sense, that might be satisfying to you. I'll fill in some more details in a second. Because these coefficients represent sort of the strength or like intensity of how you're breaking up your function into these special XOR functions. So it's sort of reasonable to imagine that you might only want the important ones. You know, if you like, you know, mash some like note on your keyboard, maybe there's all sorts of crazy overtones and so forth. But you really, if you're trying to understand it, you only maybe want to detect like the 3 main notes that were played, for example. And that's kind of what this Goldreich-Levin algorithm can do. Now I have to explain a little bit what I mean by large. And to that, I have to tell you a fact, which you'll have to just take my word for. And this fact is, if you add up all the like Fourier coefficient squared, it's always 1. Okay, this is like a math fact. It's not too hard to prove once you properly know what the definitions are. So actually, let's just check that. If you go back to this function, you know, I'm telling you to like take all the green numbers, square them, and add them up. So you get 0 squared is 0, half squared is a quarter, half squared is a quarter, half squared is a quarter, 0 squared is 0, 0, 0, minus half squared is also a quarter. So you add them up, you get 1. Great. And I think the same thing holds even for, well, I know the same thing holds even for like the AND function, where I had like negative a half, negative a half, negative a half, positive a half. It's actually the same set of numbers, basically. If you square them and add them up, you get a quarter, 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 quarter. It adds up to 1. Okay, so that's a basic fact that you need to know. And that kind of tells you the overall sort of scale of these Fourier coefficients. They're always, for a Boolean function, when you square them, it always adds up to 1. And so, so you can say, like, you know, if I define large to mean that the, let's say the absolute value of the coefficient, the absolute value of the number is at least, let's say 0.01. Okay, and I put the absolute value because it's also important to know, like, not just which ones are big and positive, but which ones are big and negative. If I say, like, this is the definition of large, then I claim there actually cannot be, you can never have too many large coefficients. So maybe somebody can tell me how to finish this sentence. Then there are always at most blank many, quote unquote, large coefficients to find. Okay, I'll peek up at the chat. 10,000, yes, excellent. That's very good. That's right, because if, you know, if your threshold for large is this is 1 over 100, that means the large coefficients, when you square them, that means like the coefficient squared, when you, if it's quote unquote large, is at least 1 over 10,000. But we know that all the squared coefficients add up to 1. So you could not have more than 10,000 of them, which are at least 1 over 10,000. Okay, and 10,000 is not a very large number. That's fine for your computer. And so what that means is like the existence of this Goldreich and Levin clever algorithm is plausible. If you say set your large threshold to be 0.01, there are only at most 10,000 different important coefficients to find. And so what a Goldreich-Levin would do, let's say for this majority example, okay, it's a very trivial example because there's only 8 rows, but the Goldreich-Levin algorithm would say like, aha, here are the important ones. Actually, let me draw it on this one. Say like, here are the important ones. This one, this one, this one, and this one. Like I found the large ones. Okay, so whenever on the right-hand side you had at least 0.01 or less than minus 0.01, it would find them. And by the way, the meaning of this, the left-hand side here is like, this is the strength or intensity for XOR of 1, 2, 3. This is the strength or intensity of XOR on just 3. This is the strength or intensity of the XOR function on just 1. And in general, like the meaning of the left-hand side is it's the XOR function on the bit positions where you've written a 1. But again, it's not so important. It's just these are also indexes for the 8 different special XOR functions. Noah Singer says, reminiscent of Markov's inequality for a random variable with variance 1. Exactly. It's sort of, it's, oh, so true. But let me not, yeah, I could get talking about such things forever. Yeah, it's like Markov's inequality for the random variable being like the square of the coefficient. Okay, so that's something that's a cool algorithm that Goldreich and Levin came up with, and then 3 other computer scientists called Lineal, Mansour, and Nissan a couple years later had a great idea that you could use their algorithm for machine learning, and you could like use it as like an attempt to like do some machine learning. Now it's sort of a little bit basic, but if you take this idea and add some bells and whistles on it, then it's actually pretty useful. So what is the deal with machine learning? I'll just draw a hilarious like 1-minute explanation of it. In machine learning, like maybe you have some like data sets, like images or something. So maybe they're like 2-dimensional images with like pixels. And each pixel, let's say they're black and white images. And so you can store them as binary strings. You just list off the pixels, whether 0 or 1, black and white. And maybe like you have like some picture here. And the learning algorithm is trying to decide if it's a picture of a cat or not. I don't know why that's the traditional example. So you kind of imagine that there's some program out there that can like take as input like a picture represented as a string of 0s and 1s if there are n pixels, and then it's supposed to output like +1 if there's a cat in the picture and -1 if there's no cat in the picture. Okay, and somehow we kind of know that this is sort of possible because like our brains sort of can do this function f. Our brains can like take in a picture and like output yes or no, there's a cat in there. Okay, maybe there's some edge cases if it's kind of hard to tell if there's a cat or not. But the idea with machine learning is like we know there is some classifier out there, f, and we kind of want to come up with one by just not programming it ourselves, but like getting like tons of examples. Like we'll just download a ton of pictures of cats, download a ton of pictures of not cats, and hopefully figure out like a replacement for f, that we can like build our own replacement for f. And the lineal Mansour Nissan idea is like the following: like we kind of have the ability to execute f because we can like for any input picture that we care about, we can kind of like ask a person to just tell us like, hey, is this a cat or not? So it's kind of like we can have a program for f, and we're like trying to like extract from it, like figure out our own program for f. So like the step 1 is use this Goldreich-Levin algorithm to find the like large Fourier coefficients for this f. Because this Goldreich-Levin algorithm, like if you have the ability to like, run a program for f, which we kind of do if we get humans to like label pictures, then they tell you you can figure out the Fourier coefficients for this function. Okay, and so it might tell you, okay, this function f has like 0.6 intensity on some XOR function of the pixels, and maybe some other intensity on like some other XOR of the pixels, and maybe like some few other intensities. Okay, maybe it'll come back with like 10,000 different intensities. And then, you found all the large ones, but there could also be a lot of other ones that are maybe important, but you just kind of hope that they're not important. So you just like treat the remaining, or imagine that the remaining 2 to the n minus 10,000, coefficients are 0. So you imagine, okay, like f could be like perfectly decomposed into like 2 to the n many different XOR functions, but we're just going to find like the 10,000 most important functions, keep that part, and like sort of just zero out all the rest of the part. And then like this stuff here is like something that you can compute. This is like your trained algorithm. If it's given like a new picture with pixels, you just plug it into this algorithm that that has these different strengths on these different XORs. And, that'll give you an output that's a real number. For every input, this will map an input picture into like a real number. And, hopefully, like for a given input picture, hopefully this real number will be like, I don't know, like 0.9932. And then you're like, oh, in this case, I'll predict that it's a cat. Or it'd be great if it like, predicted some number like minus 1.0024, in which case you'll predict not cat. And how'd you manage to like, get literally all the Fourier coefficients, and you'd be like sort of recovering an exact representation of the function f, and you'd have like a perfect predictor that always correctly output cat or no cat. But like you're just sort of hoping or banking on the fact that like, most of the important coefficients are there's only a few like important coefficients, and then like lots of coefficients are 0 or very small and not important. And if that's the case, then this kind of algorithm can kind of work well. And you can actually prove theorems that say that like this kind of algorithm does work well for some simple kinds of machine learning classification problems. And for more complicated ones, like telling cats, it like doesn't actually work well. But if you combine it with more like learning ideas like kernels and other things, then you can actually use this idea kind of effectively. Any questions about this? Oh, next week we're going to talk about pack learning. Great. Oh boy, so great. All right. I want to just, I feel I don't have that much time, but like, let me say something real quick just to pique your interest, which is this. I told you that for any Boolean function, if you square all the coefficients and add them up, you get 1. And this Goldreich-Levin algorithm will, if you have access to the program f, it'll find the large ones. But unfortunately, it could be the case that there are no large ones. It could be that like every coefficient is like 0.00000000003 or something. Like all these coefficients could be like less than like 1 over a trillion or a quadrillion. And then the Goldreich-Levin algorithm will just be like, I didn't find anything. And you'll be like, I don't have a lot of information about this f. But here's a wild fact that I'll just tell you to pique your interest. If you have a quantum computer, you can do something way better than the Goldreich-Levin algorithm. And I'll just say this and then leave you intrigued. A quantum computer can do something much cooler. If you have a quantum computer, then given like a program for f and like the ability to build a quantum computer, it can quickly do this task. It can like very easily do this task. And that's output a random x, kind of an index to it. Maybe I'll call it s. Well, yeah, let me just say x. X in 0, 1 to the n, where x has probability f hat x squared. So you know, like if you have like some function f, it's got all these values, +1, -1, +1, ... The Fourier coefficients are like some like numbers, 3 minus 0.00002, ... And we know that if we like square these numbers and like add them up, we get 1. And if you have a quantum computer, then like you say, quantum computer, go. And it'll return a random row. And the probability of it returning a particular row is the square of the Fourier coefficient. And that makes sense. Well, it's plausible that it makes sense because the square of the Fourier coefficient is a non-negative number. And I told you this fact that the squares add up to 1. So like, probabilities are supposed to add up to 1. So it actually makes sense that, these squared numbers form like probabilities. And a quantum computer can pick out a random string, like a random row in the Fourier coefficient table with probability given by the squared Fourier coefficient. And you might be like, is that good for something? And it turns out, yes. It turns out that like using this, you can like crack almost all cryptography schemes that are in use today if you can build a quantum computer using this weird thing about Fourier coefficients. And furthermore, there's a sense in which like this is the only extra power quantum computers have over our regular computers. Doing this like Fourier coefficient, pick a random thing with probability equal to the squared Fourier coefficient. So now, I mean, you kind of know what a quantum computer can do. Okay, so there's a couple of questions in the chat. Let me go over them. So one question is, does a random function have low expected number of large Fourier coefficients? Because a random function is hard to learn. Very good. Great question. If you pick a random Boolean function, like you just fill in the truth tables with random plus or minus ones, then indeed, all these Fourier coefficients will be like super tiny. They'll all be sort of plus or minus square root of 1/2 to the n. Kind of like this, maybe with some slight fluctuations. I say square root of 1/2 to the n because they have to have this property that if you square them and add them up, you get 1. But they will be like incredibly tiny. So, they'll consist of like the, if n is 100, it'll be like 50 zeros in a row in the decimal expansion and then some digit. And that's why indeed like a random function is hard to learn because like Goldreich-Levin will be like, there are no large Fourier coefficients. Another question is, PAC learning usually talks about learning from samples. This is learning with queries. Yes, so this is in one form of learning. You don't really have sort of the ability to evaluate f on your favorite inputs. It's like you can't go to like Amazon Mechanical Turk and like pay a bunch of people like, please label this picture for me, this picture for me, this picture for me, this picture for me. The only thing you can do is get like sort of like a random sample of things that people have already labeled on the internet, maybe. So you can like download a bunch of things and get some labelings of images. But this Goldreich-Levin algorithm needs the ability to like be able to actively ask like, oh, here's a crazy picture, cat or no cat. Here's another crazy picture, cat or no cat. And that's a power that's it's needed for the algorithm, but it's also expensive if you really want to do it learning in learning because you usually have to like pay a human to do the labeling for you. Okay, more questions? Okay, so I'll take about, I was told this goes like 1 to 1.5 hours. So I'm gonna take about 20 more minutes. I'm not offended if you leave though. So I mean, just if you wanna go, see you later, no problem. But I'm also happy to stick around as long as possible. I'm gonna try to talk for like 20 more minutes. Okay, and so in this last part of the discussion, I'll talk about why. Like, why would you, okay, we saw a little bit about like, it's useful for learning maybe, and has something to do with quantum computing maybe, but like, let me try to answer a little bit more about why you would care about the Fourier coefficients. And the main reason you might care is it turns out that a lot of interesting properties of a Boolean function are sort of summarized by its Fourier coefficients. So a lot of like interesting aspects of the Boolean function can be easily figured out if you know the Fourier coefficients. And so like mathematically, it's very nice to like imagine or figure out what the Fourier coefficients are because you can learn a lot of things about the function f. So I'm going to try to give some examples of that. Let's do it. So for example, let's go back to my favorite example, majority of 3. And now I'm going to like annoy you a little bit further. So, you know, I used to say like, okay, the possible inputs are 0, 0, 0, 1, 0, 0, etc. And then I said, oh, I'm going to make the outputs be -1 and +1. Now I'm going to annoy you further and make the inputs also +1 and -1, for a reason you'll see shortly. So hopefully that's not too annoying. So now I'm going to think of the inputs as like minus, minus, minus. I'm not going to write the ones. Plus, minus, 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 plus, minus, 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 plus, 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 minus, plus, minus, plus, minus, plus, 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 plus. Okay, this is my picture now of the truth table of majority of 3. And let me write over here also the list of Fourier coefficients, which we saw before, but I'll write it again. It's like 0, 0.5, 0.5, 0.5, 0, 0, 0, minus 0.5. Okay, so I just want to tell you some facts about the Fourier coefficients and how they encode like some kind of interesting information about the function f. So here's one fact. The first entry, here's a fact. The first Fourier coefficient, I mean this one, is equal to the average value of f of x. Okay, and you can check that that's true. So apparently the average value of these, the average of these red values is supposedly 0. And that's true. Half of them are minus, half of them are plus. Okay, so that's kind of cool. Like this first coefficient always sort of tells you how biased the function is to being like +1 most of the time or -1 most of the time. Okay, so that's nice. And I can give you several more examples, and it's easiest to describe these examples when you think of the function f not as like a circuit or like a cat classifier, but when you think of f as a voting rule. So I'm going to talk for the rest of this, talk about some voting theory, some social choice theory. So let's think of f as a voting rule, and I'll explain a little bit what I mean. It's a rule that maps like the votes in an election to the winner. So the situation is that we're going to have 2 parties. So the 2-party system in this voting world called minus and plus. You can associate them to your favorite parties, however you like. And you have n voters. And now a Boolean function. So now I annoyed you by making both the inputs and the outputs be like plus or minus. So it maps like -1 plus 1 to the n into -1 plus 1. So it maps a list of n bits into an output bit. What it's doing here is it maps voters to the winner of the election. And you might say like, wait, so you mean it just like takes the majority of the input bits? Well, not necessarily, because in real life, you know, people don't always use majority votes like first past the post as like their election scheme. It's very interesting in like the study of social choice theory to think about and compare different voting rules. And it's not always about like elections with political parties too. I mean, also people need to have like rules if they're like, I don't know, like a board and they want to decide whether to pass a motion or not pass a motion, they have some voting rule. Or if you're, you know, a department and you want to hire some person, you have to decide whether you're going to hire them or not. You have some kind of voting rule. So it's not always just majority. And so this field of social choice is about maybe studying and comparing different voting rules. And it turns out you can do some interesting analysis of voting rules using Fourier analysis of Boolean functions. So that's the last thing I want to talk about. But let's imagine some very different, various different voting rules. So, you know, the most famous voting rule is indeed the majority vote. Okay, you just look at all the n input voters, and the winner is the majority outcome. So I'll call that majority sub n. It only makes sense when n is odd. If n is even, you have to invent some tie-breaking rule, but never mind about that. And it's actually surprisingly hard to find like a country whose president is elected according to direct majority vote. Like, strangely enough, very few countries have this property. My best example is like, I think Mexico more or less has this property, but not exactly. but it is close to being the case in Mexico that just you vote for everybody votes for president, and whoever gets the most votes wins. But that's not the only rule. So many countries have some kind of like two-tiered majority. So this is, for example, the case in my home country of Canada, and also in like the UK and many other countries. And what's a two-tiered majority? Well, you have like all these voters voting for, well, one imagines just like two parties. Although usually in these countries there's more than two parties, but never mind. And the voters are grouped into like something called ridings, which basically means like a county. And you like take the majority vote on like this like riding level. And they're not even necessarily the same size. Take the majority vote on all these things, and that sort of gets a winner for each county. And then like the prime minister is sort of like what you get when you take the majority of the winners of the counties. Well, this doesn't make sense because I've drawn 4 counties here, which is even, but never mind. As you may know, it's coming up. In the USA, there's something called like the Electoral College, which is kind of like this two-tiered system where like these are the states, but there's like an extra twist in the Electoral College where the states have like weights. The bigger populous states have like different weights. So like if you're like Wyoming, this is Wyoming, your vote counts for 2. And if this is like New York, your vote counts for, I don't know, 40 something, maybe and so forth. So, and this is some kind of like weighted majority. That's the Electoral College. Okay. And there are other schemes, like a funny scheme that is unfortunately used a lot in practice is the Dictator Scheme. So the Dictator Scheme is, it's kind of like the sham election. So like everybody votes, the end votes happen. And then like the output is just the first vote. The dictator, whatever they vote for is the answer. And that's the function that's like f of x1 through xn is x1. Kind of a silly function, but it exists in some situations. For example, Sudan, he's the dictator of this course, from what I understand. No, actually, I mean the country of Sudan. I guess until recently they had this dictator al-Bashir. Actually, I don't know if it's a dictatorship still, but it was until recently. And there are other kinds of voting rules like 2/3 majority. And for some things you want like unanimous consent. And that's kind of like the and function. Okay, there are many other voting schemes. And in the theory of social choice, they like to try to compare them. Ties up, time's up. Oh, I hope that's a joke. Haha. Yeah. Oh, I'm going to go on and talk into the void. Okay, I got a smiley face. Yeah. Yeah, in the theory of voting and social choice, you can try to kind of just like mathematically compare them and try to learn different facts about different voting schemes. And you can do that in many different ways. And if you're like very mathematical, then one way proposed by mathematical economists is to consider different voting rules under what they call the impartial culture assumption. It's a very fancy name these economists came up with, impartial culture assumption. And this means you imagine that the votes are random. That's exactly what it means. So you just imagine that all the voters like flip a coin to make their votes. And then you can start reasoning about like the probability that different voting rules have this or that property. You might think this is kind of ridiculous that like people don't just like flip a coin for their votes. But actually, on one hand, like you got to do something. You got to make some model if you're going to start studying these things. And it's also like a reasonable model if you imagine like in the US, like maybe 96% of people's like their votes are fixed. Like it's not even a question how they're going to vote. They're fixed either plus or minus. And then maybe like 4% of people are really the undecideds. And like maybe you can model them as like being a coin flip for their votes. Okay, and so like you can take your Boolean circuit that represents the voting rule and like plug in like 96% of the inputs are fixed to 0 or 1. And then the remaining like undecided voters, you can really maybe imagine modeling them by coin flips. Okay, so this impartial culture assumption is not too crazy. And yeah, you can use it to understand properties of different voting rules. So remember this fact I told you up here. This first Fourier coefficient is the average value of f of x. That's a very, average value of f of x is a very natural concept in a voting rule, for a voting rule. it's sort of like if all the voters vote at random, it kind of tells you like who's more likely to win. It kind of describes like the bias of the voting rule. Some voting rules are not biased, like majority. It doesn't inherently favor the outcome plus or minus, but other ones like 2/3 majority, it mostly favors the outcome minus, right? Because it's hard to get a 2/3 majority. So it's like a little exercise. You can check that this first Fourier coefficient is can also be thought of as the probability under the impartial culture assumption that plus wins minus the probability that minus wins when everybody votes at random. Okay, and as I said, so actually this coefficient squared well, you can see, for example, this coefficient squared is, if it's 0, this would be like an unbiased rule. Because 0 squared is 0. It's like equally likely that plus or minus will win if everybody votes randomly. On the other hand, if the squared coefficient is very close to 1, it means the coefficient itself is either very close to +1 or very close to -1, which means that the voting rule is inherently very biased. Okay, so this Fourier coefficient, or its square, like tells you something about the bias of the voting rule, which is nice to know. Okay, so there are actually many more links between Fourier coefficients and like sort of aspects of a voting rule with respect to thinking about it, its various properties. But I'm just going to tell you one more. It'll be the last thing we talk about. And let's say there's a theorem, which is not too hard to prove, that says the following. It's a link between the Fourier coefficients and something about voting. So it says if you add up the squared Fourier coefficients, but not all of them, just some of them, over all strings x, all rows in the Fourier coefficient table, with the 17th bit being 1, the result is the voting power, sometimes called the influence, but I'll call it the voting power of voter number 17. Okay, and 17 is just like an arbitrary number I chose here. This is true for all the different voters. You can figure out their voting power by adding up all the squared Fourier coefficients in rows that have a 1 in like that voter's position. And what is this voting power? It's the probability that that voter is the swing voter. So it's the probability, let's say for voter number 17, that voter number 17's vote is like pivotal for the outcome of the election, for the election outcome. So it's the probability, if everybody other than voter 17 votes at random, that it'll all come down to voter 17's vote. Okay, and that's some kind of measure of how much power a voter has in this particular scheme. Like if their vote is never pivotal, then it's like they have 0 power. And if like, if it's a dictatorship, so let's do an example. In a dictatorship, the dictator voter, voter number 1, dictator, voter number 1 has voting power equal to 1, and the rest of the people have voting power 0. And these voting powers are always between 0 and 1 because they're probabilities. Okay, so like the dictator has like all the power and everybody else has no power under this definition. What about the classic majority scheme? Like the most simple thing when everybody votes and we just take the majority answer. Here, everybody has the same voting power because it's symmetric. Every voter has the same power. And please try to think about what it is as I'm talking here, as the same voting power. And like, what is my power in a majority, a direct majority scheme? It's the probability when everybody else votes at random that everybody else's votes exactly split, like literally 50-50. So remember, we're imagining that n is odd. So there's like an even number of other voters. And it's like, my vote is pivotal if and only if like everybody else exactly split 50-50. That's the chance that I have power, that my vote kind of counts. And so this is like a probability question. It's like the probability if you flip n minus 1 coins, what's the chance you'll get exactly half heads? Does any non-instructor know what the answer to this is, approximately? It's not very high, and it depends on n. Okay, I'm not seeing anything in the chat, so now we can open it up to instructors if they want to show off their knowledge of probability. It's an interesting question. It turns out to be approximately 0.8 divided by square root n. Actually, this 0.8 is more like the square root of 2 over pi. So incredibly, there's something to do with pi and flipping coins. But anyway, it's approximately 0.8 divided by square root n. So I think like if n is 300 million, like in the US, I don't know what the square root of 300 million is, maybe 17,000. So maybe you're like the probability that in a direct election in the USA that like your vote would be the swing vote, if everybody voted randomly, would be like, I don't know, 1 in 16,000 or something. It's actually not too bad. Okay, and so the last thing I'll do is think about comparing voting powers for different voting rules. Because it seems nice that like the voters should have the power. That seems like a reasonable thing. So let's define the total voting power for election rule F, which might be, direct majority or electoral college or two-tier majority or dictatorship, to be, just add up the voting powers. Just add up all the n voters' voting powers. Okay, that's some sort of collective measure of like how much like democracy is invested in the population. Okay, so for example, if F is dictatorship, we get 1 voting power for the dictator and 0 for everyone else. So the total voting power is 1. All right. And it's sort of at the other like popular extreme. What if we have like direct majority? Well, I told you everybody has voting power that's basically 0.8 over root n. So we get 0.8 over root n, 0.8 over root n, plus dot, 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 plus 0.8 over root n. There's n voters, and times. So we get 0.8 over root n times n. Okay, so which is basically 0.8 times root n. Okay, so if, I don't know, the US population is 300 million, maybe this is like, again, like 17,000 or something, which is a lot bigger than 1, which is kind of nice. Here's a fact that you can actually prove if you review this whole lecture and think about some of the things I've said. If the voting rule F is unbiased, meaning that it's not inherently, the outcome does not inherently favor either of the two outcomes, plus or minus 1, then the total voting power, this is a little mathematical theorem, is always at least 1. And actually, this proves that the dictatorship is the minimum. It seems funny to say, but like according to my definition of bias, dictatorship is unbiased because in the impartial culture assumption, you imagine that even the dictator votes randomly. So even with dictatorship, the outcome is equally likely to be positive or negative. But it shows that this, this calculation and this fact show that the dictatorship is sort of like the worst in terms of investing power in the voters. There's a famous theorem that got me into analysis of Boolean functions when I was a graduate student back in those days, working with Madhu, by Khan, Kalai, and Lineal. It's kind of about voting. It's from 1988, and it's a very famous theorem where basically the only way to prove it is to use analysis of Boolean functions. So it's like a real example of what it's good for. And they prove the following. If F is an unbiased rule, and let's also assume that like all the voters have the same power. Okay, so to get rid of like dictatorship, but that still doesn't mean it's majority. It could be like a two-tiered majority where all the groups have the same size. That's one example. So in this case, they prove that the total power the total voting power is more than 1, it's always at least about log n, the logarithm of n, which is bigger than 1. So these are kind of like the more reasonable schemes. You're not only unbiased, but everybody has the same power. That means the total power has to be at least the logarithm of n, which I guess logarithm of n for n being 300 million is, I don't know, 25 or something. And actually, there's some bizarro voting scheme that has this property. It's something like you divide up like all the population of the USA into like groups of 25 people. And if one of these groups unanimously votes for like Democrat, then the winner of the election is Democrat. And if no group is unanimously in favor of Democrats, then the winner is Republican. And if you set that number 25 carefully with respect to the population, you get like an unbiased voting scheme where all the voters have the same power. It's a very strange one, but like all the voters have very little power, it turns out. Okay, so last thing I'll say, this is really, I'm wrapping it up with this last theorem, which is one more theorem, which is not too hard to prove. You can prove it again using Fourier analysis of Boolean functions. Say f is a voting rule which is unbiased, which we like, and monotone. You might talk about monotone Boolean functions in this course, but basically a monotone voting rule is one where you should never vote against the candidate you care about. Like if you want plus to win, you should always vote plus. And if you want minus to win, you should always vote minus. And like it's all the reasonable voting schemes have this property. It's like bizarre to not have this property. So this is a pretty natural class of voting rules, unbiased and monotone. Then the total voting power is at most this 0.8 over root, 0.8 times root n. Or more accurately, this root 2 over pi times root n, or even more accurately, it's like literally the voting power of majority. In other words, among all these, simple voting rules that are unbiased and monotone, direct majority is the voting rule that like gives the most power, most voting power to the citizens. Okay, so there we can